Welcome to the next tutorial about the next steps in our nice project. So what did we do until now? We read the data. So we took an Excel file or different Excel files and we read the data with different methods. So we used XLS read, we used read table, and we used load. And then we processed the data and we plotted the raw data. Finally, we calculated an aggregation, which means that we took 15 minutes steps, and then we calculated the mean, the normal arithmetic mean for that, so that we got a nice step function which represented a smoothed data set of the original data set. And now we have the situation that the data are not always correct. In our case, if you have a close look, especially in one data set, then you will see that there are a lot of -1s in the speed values, which cannot be. So first of all, it's always quite difficult to deal with these special outliers. You have to know that there are outliers. For example, if you just have data sets where no outliers are included, it's difficult that you will think about that there are outliers. And then you have to find a possibility or a method so that you can deal with these outliers, so that you can avoid the outliers, or that you can use the rest of the data correctly, things like that. It's always not so ideal if you create your own data or if you manipulate the data so that it might fit. So you should not create new data. And therefore, we start today with the idea of this outlier problem. So what is the background of these outliers? Why do we have these outliers? And then we have to find a way to delete these outliers. In the project description, you will find also another thing, which is Q-weighted mean. So therefore, the next task will deal with this Q-weighted mean. So we will calculate a Q-weighted mean in a function which you can use in the same way like the normal mean. And then we use this Q-weighted mean for calculation, and then we want to compare these three different methods. So the thing which we calculated before without outlier detection, then the outlier detection aggregation, and then the Q-weighted mean calculation aggregation. And then we compare this and we'll see that there are big differences. So let's start with this outlier problem. If we read the data again, then ts read table, for example, step by step is our function. If you read the data again, and if we plot the speed data for the first sensor, then we will see that there are these outliers. So if we do a plot here, for example, plot speed 1, colon, then you will see that we will have these outliers in the first part of this section. So have a look at it. It's here. There are a lot of -1s, and a speed of -1 is not possible. You can also find these outliers if you do the following. If you do, for example, indexes, and you use the function find, and tell that speed of 1, colon is lower than 0. And then you will get all of the indexes where you have a minus speed. And you can directly check what is the minus speed. You can say speed 1, indexes, and then you will see that all of these outputs are -1. So what are these -1s? These -1s are detector errors. It might be that there are error representations. So, for example, it cannot happen that you have a minus speed, and therefore the customers or the vendors, the vendors of the product might code special error situations with minus values. So, for example, it might be that there are minus values for different error situations, and it tells you that at this moment there was no detection, or there was an error in the detection, or there was something different, and therefore we have to avoid these minus ones, and therefore we have to improve our plot. So the answer for question or for task number 1 is that we will have these minus ones for error situations, and therefore we want to avoid these error situations. So what we do is the following: we create a new file for a script called TS aggregation outlier, and in a first step we do nothing more than copying the existing mean calculation into this outlier script. And instead of calling TS plot, we call our TS aggregation. You see, we always call our previous script so that we have a sequence which is operated in the different steps. We also want to create a new window. So we are now in window 3. And then we have to improve this part here. So in this case, we have to delete our values which we don't want in our calculation, and therefore we have to do a separation. And this can be done quite easily because we already have 2 steps here. So we have the selection, we have the mean calculation, and then we have the assignment. So what we can do is we can create a separate sequence of the original data, which we call participating vector. And in this participating vector we have everything, the outliers and the original data. And then we can use a very simple selector mechanism in Matlab, which we already know. We used it already here. So if I go back in this style, we already used this mechanism where we define a condition and only this value will appear. So we do the same here. So if the participating vector here, or the values in the participating vector, are lower than 0, then delete this element. And if we delete this element, the vector size will shrink. And if we now use this shrinked vector, so this reduced vector instead of the original vector, then we have the complete calculation finished. So in this case, we have now a situation that all of the data which are not used, so everything what is lower than 0, will be deleted and will not participate to our final mean. There is one problem. Do you see it? What happens if all values are deleted? So in this case, it might be that there are only minus ones in our interval. Therefore, we have to do a special exception. And this special exception can be done with an if statement. So, for example, if we have no length anymore, so if all elements are deleted, then give a warning. And define a specific value which is the result of the aggregation. And here it's quite a problematic situation, because if you just assume that the mean value is the same like in the previous one or in the next one, then you have this manipulation of the data, and therefore I would suggest that you use the same technique what is used by the sensor. So if you have only -1s, then define the whole block as -1. So what you do is you assign to all of these elements the -1 again, so that you have the same situation as before, because you had just -1s, they were completely deleted, and therefore you fill it in again. So the final mean is -1 in this case. And then we have the else part, and in the else part we do the normal reduced aggregation with the reduced set. And then we can clear our participating vector because we won't need it later on. So with this, we have now prepared a new version of the mean calculation where we have deleted all our minus values. Let's run it. So we load the data and plot the raw data and plot the aggregated raw data and plot the aggregated and raw data with this other version of calculation. So if I then look into the data, you will see that it looks quite similar to what we got before, and there are just small slight changes here which you directly see. Maybe if you compare these things, here are lower mean values than in the other. You will see it in more detail in the task, or for the task of the comparison. So this is the task to avoid the outliers. So in the next step, we want to do the next mean calculation, which implements the q-weighted mean. Therefore, we have to first find out what is the q and where do we find it, and then we have to integrate it in our calculation with an own function which is named qmean. So let's do this. Where do we find this stuff? If you watch the project description, you will find this image. So the Q or QH is the traffic volume at the main lane or on the main lane, and therefore we can use this, and we find it on the 4th position. So we have the time, we have the speed which we already use, then there's a smooth speed, and then there is this Q. So from the 4th position on, and then each 8th column, so that we can use this like already known with the speed. So what we have to do first is we have to extract these Q's like the speed vectors or the speed matrix from the raw data. So let's start with TS read table. TS read table looks like this. And here we have to add at the end, for example, the extraction to get the traffic volume at the main lane, from the main lane. In principle, it is nothing more than this, so we can copy this and we just replace all of the speed cell matrices with Q matrix and all of the speed with Q matrix. So we have here then Q matrix cell matrix and Q matrix, for example. And we do not start here at the 2nd column, we will start at the 4th column. So if I do this, I just copy it and I do exactly the same steps. So with this, I have now, instead of the speed cells, I have the Q cells, and instead of the speed matrix, I have the Q matrix, and I start at column 4. So if we run this, you will see that we'll get an additional matrix, which is the Q matrix. So it appears then here. And it contains all of the Q values. If you watch the raw data table, then you will see that the Q vectors, so I have to go to the last position here, so that the Q vector here is the first one here. So this is correct. What we should not forget is that we have to do this for all of our read methods. So not only for TS read table, but also for TS XLS read and for TS load. So for all of our scripts, therefore we have to adapt also these scripts. And it's always the same procedure. So as we already know how it works, we can just copy this and replace it with the new name of the Q matrix, and we have to start at another position. So let's do this. We just add the same like for speed for Q, and if we run this, then we'll get a correct result, and the same for load. So here is our original load, and we just copy this part here. Don't forget the difference again between German style Excel output of the text data, which contains a comma instead of a floating point. Therefore we have, if you have the German version like I have to go each 9th position. If you have the American style representation, then you can use this one. Well, we have to do exactly the same. So we add the same stuff, but instead of speed, we use now the Q and start on the 4th position. So now we have everything what we need for the Q calculation. Now we have to check how do we calculate the Q. So let's go into our project description again. And in the project description, you will find this formula. So this is the sum over the speed times the Q, element by element, and divided by the sum of all Qs. So if you watch this first sum, it's something which you already should know from our vector multiplication. Of course, you can calculate, let's say, for loop, so that you go through all of these 15 elements, for example. This is our size of the aggregation. So we go through all of these 15 elements, and then we multiply each single element. Or you can use an element by element multiplication and then sum it up. There are different methods, but another one is, if you know this, then it's nothing more than a vector multiplication. So if you have a speed vector as a line vector and the Q as a column vector, then you can directly use just the normal multiplication of vectors to get the result, because it's exactly the same. So it's the element 1 multiplicated, so element 1 multiplicated plus element 2 multiplicated of both, and so on. So you have exactly this. And here you have the simple sum, which you already have available in Matlab. So therefore, this is a vector multiplication, and this is a sum. So dividing the vector multiplication by the sum. So what do? We create a new script file, and here we write the first function. And the function is called qmean. So here is my script, and we start with the function description. Function, it's the reserved word. We return one single element, which is the mean value, and our function is named qmean, and it will need, of course, the vector of the speed, the section of the speed vector. So I call it participating vector, which is the participating vector in the speed matrix, or in the speed vector, our 15 elements which we want to mean up. And the names here are just available within this function body then. For the qmean, we need another vector which we created before. So the matrix which was created before was the q matrix, and therefore we will need the participating q vector. So, and with this we can do now the calculation. So we give a short comment so that if we call help, that we know what it does. Calculate the q-weighted mean, and then we can do the calculation. And the calculation is quite simple. We do mean val, which is the return value, and then we do the matrix multiplication. Again, speed vector as a line vector, q vector as a column vector. So we use the participating vector and the normal matrix multiplication with the participating q vector, but here in a transposed form, because we expect two line vectors here. And then we divide this by the sum of the participating q vector. So compare it again. It's exactly this. This is the vector multiplication here, and this is the sum of the q's. So quite nice, everything finished. What you can do is you can add a return. It's not necessary, but you can do so that you have a block scenario from function to return, which tells you that this is the block of the function. We have now one problem. What happens, or how does the vector look like if you have the -1 situation? So what do we do here? So therefore we have to check this again. So we still have the speed matrix in our memory, so in our workspace, and therefore we can do the following. So you know it from the beginning of this lesson. So we find all of the speed values where the value is lower than 0, and return find always returns the indexes. And therefore we use these indexes as vector for the new selection in the Q matrix, so that we see the values at the corresponding positions where speed is -1. And here we see that it is 0. This is quite nice, because if you watch this, if we just have single -1 situations, then it will not participate because it's 0, and 0 times something it doesn't matter. So we don't have to take care on this, but we have to take care on if all of the elements in the participating vector are zeros, because then the sum will be 0, and then we will have a division by 0. So what will be the division by 0? If we do 0 divided by 0, then we will get not a number. And this situation we want to avoid. Therefore, we have to do another exception here. So for example, if this sum is equal 0, then we will return what we already know, mean val equal -1. So we return a complete -1 block, so that the mean value is a representation for the error situation. So we have now, if this happens, then we have -1, else we have this calculation, and we don't have to take care on the rest of the outliers, because the outliers are automatically avoided due to this calibration of the participating vector, which is then 0, because if there is an error, we have no count of the density on the main lane. And with this, we have now a function which we can directly call. So if we save it, and if we then write qmean, then we can use it with the input values. Okay? And here you see qmean, participating vector, participating q vector. If you push more help, then you should see the additional information. So, how can we use this now? In our case, we have to now extend or change the aggregation again. And therefore we create a new script file, and this new script file will be nothing more than a copy of the original aggregation. So let's do this. So we create an empty file, which is now named ts aggregation qmean, and as a first step we copy in the original aggregation, with the only difference that here we want to call the previous aggregation with the outlier separate avoidance. So therefore we call ts aggregation outlier. Sorry, it did not work. ts aggregation outlier. ts aggregation outlier. Okay, and we want to create a new figure, so we created figure 3, therefore we create figure 4 here. And now we have to change this again. So what do we change in this position here? It's quite simple, because as we have already the setup, and as we don't have to do the avoidance of the outliers, we can just replace this by the qmean, and we need two arguments. The first one is the speed vector, and the second one is the q matrix with the same interval. So the indexes are exactly the same. So we just add the same what we did for aggregation, we add for q matrix. In this case, we can use the original because we don't update this matrix, so we can directly take the q matrix. We don't have to create a copy. And this is all. So with this, we have now a complete set of the calculation. If we beautify the outputs, plot aggregated data and raw data, and maybe we use qmean in addition here, then we also find a nice output, what and which aggregation is called. So if we run this now, we should get all of the possibilities. I use load because it's faster, and then we'll get a plot of the raw data, then we will get an aggregation with arithmetic mean, with a mean without outliers, with a qmean. And the output will be this. We will have now 4 figures with the different outputs. Sorry. So these are our outputs, and with this we solved task 4 and task 3. So you see, it's quite simple. It's always a step-by-step adaptation, and if you have a first version of the script, then it's quite easy. So therefore, we can now check how good our calculations are. So we do a comparison between the different mean calculations. We check the original mean compared to the mean without the outliers and compared with the mean using the Q weights. As we know that the first sensor has the most outliers, therefore we do the plot just for the first sensor. And we have to find a way to do this comparison. A problem here is now our method of using scripts. Therefore, one of the next steps must be to create all of these things into functions. But you should see where the differences and the difficulties are. Which problems do we have? We have to do some, let's say, compromises. If you watch our scripts, we always start with this clear all, close all in CLC. And this means if we call our 3 scripts in a sequence, we will delete the things or we will override the things because we have the same naming conventions. And each time a new script is called, it will override the previous one, or it will override or it will delete the previous things. So if we call it in a sequence, we will delete things. If we call it always in this nested way, we will override the existing aggregations. And now there are 2 possibilities. You can update the different scripts so that you give an individual naming. But I want to show you also another possibility, another method, which helps you to store the information which you need later on persistent by using the save function. So let's do this. So we create a new script, which is now a little bit a separate script from the others because we will maybe not use it later on. But in our sense, we can use it in the same style as all of the other scripts. And then we start again with a clear and close and CLC. And then we can do the following. We can call our different scripts. For example, here's aggregation step by step. Problem here is now that if I call the scripts, all of the other scripts will be started again. So it will last much longer. But why I do this, I want to show you how to remember information even if the information is deleted through the process from the workspace. So what I do here is I run the script, and after the script, everything what the script created exists. Therefore, I can make a copy of that. And if I have a copy, I can save it in a file. And if I don't save it as a text file, if I use the Matlab binary version, I can save the matrix with the complete name. So it saves everything what corresponds to this matrix. So therefore I make a copy and I save this, and the name of the matrix is also saved. And I do this now for all of the different calculations. So in the next step, I run the next script. So TS aggregation outlier. I copy the aggregation again in a new matrix. Then I load the previous file with the standard Matlab version. So therefore TS aggregation will be created again because in this file the name is still saved. And then I save it again. And I save again now the TS aggregation and the TS aggregation outlier. So these two matrices again with the binary Matlab version of the file. And then after reloading it, I will have these names available again, and I have everything in one file. And then I call it finally again. So if you don't want all of these aggregations in one sequence, you can also just always call the tsplot instead of the previous aggregation script, and then this script will still work. It will not last so long anymore, because here, for example, also the TS aggregation and TS aggregation outlier will be calculated, and here TS aggregation will be calculated. So we do all of the steps several times. But it's a quite nice thing to show you how to remember things using files where you have the extracted data available. So in the last call, I do the TS aggregation qmean. I copy the TS aggregation qmean so that I have a copy of the aggregation, and then I just load this file which I created before, so that I have now, after this load, TS aggregation outlier, and TS aggregation qmean. So and now we have everything what we need. So we can now plot the comparison. Of course, we write here again a nice output, compare means, and we create a new plot. So we created until now figure 4, so we are now in figure 5, and we do nothing more than a simple plot. We already have time available. We plot speed in the known version, but just for sensor 1, because we just want to compare the data of sensor 1 in this task. And we want to plot it in blue. And then we plot the next version of our data, which is the normal aggregation. So we plot TS aggregation, also just sensor 1, and we want to plot it in red, and so on. So we plot outlier and we plot qmean in green and in yellow. And finally, if you want, you can also add a nice legend so that you know what the different colors represent. Check the theoretical lesson, how you create a legend. So each of these arguments define the corresponding text which represents the data. And with this, we have now everything what we need for the calculation of the speed comparison and mean comparison. So let's run the program. So we do a selection again. I use load again because it's much faster. And then we do all of the plottings. You see, all of the scripts are operated several times. So this is the second call where I read the data again for the arithmetic mean and the mean without outliers. And then the final where the qmean is calculated. And the result after the final call will be an output of 5 figures, where the fifth figure will contain the comparison of the means. And it looks like this. And you already see the differences here. So if I zoom in, for example, at this position, then you directly see the large differences of the different means. The blue is the raw data setup. Then the rest of the plots of the lines represent the smoothed outputs. The red is the normal arithmetic mean, and you see that the outliers really influence our mean. The green one is the arithmetic mean without outliers, and the yellow one is a little bit a smoother mean, which more represents the version of the real situation. So you see there are a lot of differences, and you also see that wrong data will influence or will really influence the output and the results. So therefore you should always take care on how the data are. You should always take care on using real values. You should always take care on things that you don't interpret data which are not trustable, and that you don't create data. So you should always take care of this, and you should always create some, let's say, exceptions that special error situations are avoided. What you also see here is our not so nice step function, because you see here in the zoom that they're not really rectangular steps because we use the normal plot. It would be necessary to adapt these connection points here so that you have the same x for the different positions, so that you have really a step to the next level. But for our representation here, it should be enough. If you have time and you feel free to play a little bit with Matlab, of course you can improve this. You can create a vector again in the time vector and in the speed vector and also the mean vectors, which contains a repeating of the x-axis and of the same corresponding y value, so that you can use plot again in the same style like before, so that you really have a nice step function. Or you can create or you can use the line function, which you also find in the script. So with this, we have everything prepared for the next steps, and therefore we have to look into the tasks for the next week. As we're close to Christmas, I want to do something which is not directly related to our project, but is related to transportation systems at all. And it deals with graphs and finding paths through graphs. And there is a nice game or a nice drawing which the kids in Germany do in the Christmas time, and it's called the house of Santa Claus or the house of Nikolaus. And this is this house, and in principle you have to draw this house so that you don't have to interrupt your line. So you start, for example, here, go 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 here, and go here, so that you don't have to interrupt. This is one solution what I showed you before, and you should not interrupt this. And therefore there are different possibilities and different solutions, and the principle behind is nothing more than finding all possibilities in connected graphs. These are graphs, so each of these connection points are the nodes, and each lines between are the edges. So you have a graph where you can find a way through, and you should find all possibilities. So therefore you can find, of course, an algorithm, and you can, of course, write a program. And a first task is now you should simply draw this house of Nikolaus using lines. So just draw it, create a vector or two vectors, x and y, so that this house of Nikolaus is drawn. maybe take care in this that it is drawn without an interrupt of your movement. And that's the first task. Maybe resize the output so that it looks nice. Check how this might work, and so on. And then you can go into detail. For those who really want to play with Matlab, it's a nice task because it's something like a solution for the traveling salesman problem. So if you think in case of these lines here or these edges here are the bridges between islands or between some parts of a town, then you have here the connection points. We have an unweighted edge, so it does not define the length of the line, so that you don't have to do an optimization process where you have to use other mechanisms like Dijkstra or whatever. So it's just a simple graph without weights, and you should find all of the solutions. And you can do here a brute force or search mechanism, which finds all possibilities, and it directly deals with a recursion, so with a recursive method. And this is the task for the next weeks. I know this is the most difficult thing. It's for sophisticated users, and you can play with it. You can search what is recursion. You can search how this might work, so that you find out all of the possibilities, and then you should tell me how many possibilities you found. That's the task, and we'll see each other in the next lesson, which will be in 3 weeks, because you have now Christmas holidays. Stay safe, enjoy your time with your family, and I hope that you will get a lot of gifts and that everything will work in the last steps to the exam. So we'll see each other in the next lesson. Have a nice time. Bye bye.